This lecture is on chapter 4.1 through 4.4 on covalent bonding, bond strength, and bond polarity. So covalent bonds are a bond that results when two atoms share several electrons, so usually two. And so covalent bonds are the most common type of chemical bond, and they typically form between two different nonmetals. So whereas we have the ionic bond between a metal on the left side of the periodic table and the nonmetal on the right-hand side of the periodic table, here these are typically between two nonmetals, both located on the right-hand side of the periodic table. And so there's an attractive force between the nuclei, and the electrons is stronger than the repulsive forces that split them apart. So once a covalent bond forms between two or more atoms, it can form what's called a molecule. And so a molecule is where two or more atoms are joined by a covalent bond. So it's easy to visualize covalent bonds with electron dot structures forming bonding pairs. So let's take a look at these four compounds that we have listed here. So we have um, two fluorine atoms bound together. We have two hydrogen atoms bound together. We have oxygen bound to two hydrogens. And then we have a carbon bound to four hydrogens. So one of the best ways to visualize covalent bonding is by drawing the Lewis dot diagrams. So when we look at our periodic table, we see that fluorine has has seven valence electrons. So if we write the Lewis dot diagram, 1, 2, 3, 4, 5, 6, 7 valence electrons. And then around the other one as well, 1, 2, 3, 4, 5, 6, 7. So we can see that each of these fluorine atoms want to have one extra electron in order to satisfy its octet rule. So with ionic bonding, we know that these fluorine atoms can accept another electron to form the F minus fluoride ion. And that would be to form an ion, to form an ionic bond. What makes a covalent bond is you have a sharing of two electrons between two atoms. So if you share these two electrons, what it has the effect of doing is having a pair of electrons on both of those atoms. And so what it does is it satisfies the octet rule, giving you 8 electrons on both of these fluorine atoms. And so that covalent bond, which we can now draw as a solid line between the two, so that solid line indicates 2 electrons. That shows that we have 2 fluorine atoms, each with satisfied octets. All right, so the covalent bond allows us to satisfy our octet rule. If we take a look at H2, we know that each of these want a duet instead of an octet, and each of them only have one single electron. When they covalently bond between the two, they can form H2, which satisfies their octet rule by giving them a duet. Again, here for hydrogen, if both of these hydrogens have one electron, and oxygen, when we look at the periodic table, has 6 valence electrons. Okay, and I could have drawn this a little better for you guys, sorry. Here, I'll actually draw it a little better for you if I put the hydrogens on both sides. Okay, so 1 valence electron for each hydrogen, and then 1, 2, 3, 4, 5, 6 valence electrons for the oxygen. We can share 2 separate pairs of electrons. We can rewrite those as solid lines for covalent bonds. Now we have 2 electrons on each of these lines, so 2, 4, 6, 8 electrons around oxygen and 2 electrons around each hydrogen. That is a satisfied octet rule. For carbon, we have 4 valence electrons. Each of the hydrogens has 1. And we can visualize 4 separate covalent bonds now forming, which allows everything to have a satisfied octet rule. So using these Lewis structures, we can very easily visualize our covalent bonds forming to share electrons. So covalent bonding lowers the potential energy. So the larger the negative energy indicates a favorable reaction. So if we take a look at this plot here, so we have an internuclear distance when you're talking about bringing two hydrogen atoms close to each other to form a covalent bond. And so the further to the right we are, the further apart the two nuclei are, and the further to the left, the closer they are. And so we have an energy level here, so zero energy state here in the middle, and then high energy to the top, low energy to the bottom. So again, our negative energy, the more negative you are, the more energetically favorable the situation. And so you can see as our atoms come closer and closer together, they start to lower energy state until they reach the lowest possible energy, which indicates our optimal bond length between these two hydrogen atoms. And then if you were to squeeze the two hydrogen atoms even closer together, you could see that they become too close and the energy skyrockets through the roof. And so we can see at the bottom of this energy diagram, we can determine the bond length between these two hydrogen atoms. So if you remember from a couple lectures back, this was actually the way that researchers determined the atomic radius of specific atoms. So forming a covalent bond releases energy, which means it's energetically favorable. Okay, so if you have two different separate hydrogen atoms, when they form the covalent bond, they release energy. If you want to break this covalent bond to send them back to each individual hydrogen atom, you have to input energy in order to break the two apart. Okay, so you can think of those two hydrogen atoms coming and holding hands, and then you have to put energy in order to break those hands from each other. And so the energy that is released is equal and opposite to the energy that needs to be absorbed to break the bond. So there's several different ways that we can represent molecular structure. So all three of these methods here are representing ethanol, which is drinking alcohol. Okay, so vodka or Everclear. So this ethanol consists of two carbon atoms, six hydrogen atoms, and one oxygen. So you could either write a chemical formula where you simply list each of the constituent atoms and subscript for how many of each are involved. Or you could write a structural formula where you draw these single lines, which are covalent bonds between each of the different atoms. Or you could draw a molecular model, which shows the 3D geometry of how that ethanol takes up in space. And throughout the next week or so, you're going to become very comfortable in doing all three of these different representation of covalent molecules. So molecular structures can become quite complex. So if we take a look at glucose or adrenaline, you can see that they can become quite complex. So you have to be able to get very adept at being able to draw and understand these molecular drawings. So several elements exist in their natural state as diatomic molecules. So these molecules are hydrogen, H2, nitrogen, N2, oxygen, O2, fluorine, F2, chlorine, Cl2, bromine, Br2, and iodine, I2. And so all of these are in their natural state. So if you're talking about you're breathing in oxygen, if you're encountering oxygen in our atmosphere, that's always going to be diatomic O2. And so what these diatomic molecules mean is that you have a covalent bond between the two atoms. Okay, so these are, it's good to sort of memorize and just kind of understand these diatomic molecules that exist. So as an exercise to further understand how many covalent bonds each atom is likely to undergo, I ask you all to pause the video and draw these Lewis structures for the following atoms and identify the number of lone pairs and determine the number of bonds that each is likely to undergo. So knowing that, again, if we have, so I'll do fluorine, which is not on here, just an example to get you started. So fluorine, we know, has 7 valence electrons. So if we go 1, 2, 3, 4, 5, 6, 7, okay? So any paired up electrons that we have, we call these lone pairs. Okay? And then any electron that's unpaired, we call an unpaired electrode, unpaired electron. And these are likely to be bonding electrons. Okay? So any unbound electron can be a bonding electron. Paired up lone pairs are not going to bond. So we can call those non-bonding, non-bonding electrons. Okay, so I invite you guys to pause the video and draw carbon, hydrogen, nitrogen, and oxygen, identify our lone pairs, and identify our bonding and non-bonding electrons, and tell me how many bonds that each atom is likely to undergo. Okay, carbon has 4 electrons. So there are 4 bonding electrons here. So we're expecting to have 4 bonds. Hydrogen has 1 electron. But hydrogen's looking for a duet, so we expect 1 bond. Nitrogen has 5 electrons. 2, 3, 4, 5. So we have 3 bonding electrons, so we expect 3 bonds. Oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. We have 2 unpaired bonding electrons, so we expect 2 bonds. So as I showed earlier, you could either have single bonds associated with each of these unpaired electrons, or these atoms can undergo what's called multiple bonding. So multiple bonding is the formation of multiple bonds, or the sharing of multiple pairs of electrons between 2 specific atoms. And so we have single bonds, double bonds, and triple bonds. Okay, so the best illustration I can give you for our first understanding are talking about some of these diatomic molecules that we just introduced. So if we talk about F2, O2, and N2. So if we take a look to see at the number of valence electrons for each, F2, each of these has 7 valence electrons. So we have 1, 2, 3, 4, 5, 6, 7. Again, 1, 2, 3, 4, 5, 6, 7 for fluorine. So each of these fluorine atoms need 1 extra electron in order to satisfy their octet rule. So these 2 electrons here will form a covalent bond, a single covalent bond, to link the 2 together. And so that's a single bond that consists of 2 electrons. For oxygen, each of these oxygen atoms have 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So each of these need 2 extra electrons in order to satisfy the octet rule. So what we would get is a sharing of 2 separate pairs of electrons. So we would form 1 bond that has 2 electrons and a second bond that has 2 electrons. So each of these individual bonds has 2 electrons associated with it, but it forms what we call a double bond. So if we rewrite this, a double bond between the 2 with 2 lone pairs of electrons. And this double bond here has a total of 4 electrons associated, 2 per line. And if we take a look at our octet rule, knowing that each line stands for 2 electrons, we have 2, 4, 6, 8 around each oxygen. So we've now satisfied the octet rule by incorporating what's called a double bond. Now for nitrogen, we have 5 valence electrons around nitrogen. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And now we need 3 extra electrons in order to satisfy the octet rule for each of these nitrogens. So what we have is 3 separate pairs of electrons are going to be shared between the two, forming 1, 2, 3 bonds. So if we rewrite this, we have a nitrogen, 3 covalent bonds to another nitrogen. We leave that lone pair left there. And knowing that each of these lines here, each of these covalent bonds includes 2 electrons, that gives us a total of 6 shared electrons here. And we can count now 2, 4, 6, and the lone pair makes 8. Each of these nitrogen atoms have their lone pair, have their octet rule satisfied. And so this is what's called a triple bond. Okay? Single bond, double bond, triple bond. So it's a way of satisfying your octet rule without incorporating more atoms. And so we assign what's called a bond order, which is just a classification for a single bond, a double bond, and a triple bond. So a single bond is what we call a bond order equal to 1. A double bond has a bond order equal to 2. A triple bond has a bond order equal to 3. Okay? So the bond order, talking about single, double, and triple bonds, that affects the bond length. So the bond length, so the distance between the nuclei of 2 different atoms that come together have 2 different factors which come into play. One is the size of the constituent atoms, and the other is the bond order. Okay, so talking about size, obviously, if you have, so up on the board here, if you have 2 large atoms that come together, their interatomic distance d is going to be larger than if you had 2 small atoms that are coming together to form a covalent bond. So the smaller the constituent atoms, the smaller the bond length is going to be. So that's the first part. The second is the bond order. So you can think of this single, double, and triple bond. You can think of each of those sets of 2 electrons shared together as being like a rubber band holding together the 2 atoms. So the more rubber bands that you have holding the 2 together, the tighter they are going to be pulled to each other. So a triple bond is going to be shorter than a double bond, which is shorter than a single bond. Okay? The more attractive forces that we have holding these 2 together, 2 atoms together, the shorter the bond length is going to be. And so the bond dissociation energy, which we call BDE, is the energy required to break a bond. And so that bond dissociation energy is inversely related to the bond length. So the shorter the bond, the stronger the bond. So if we think about having multiple different rubber bands holding these atoms together, the more rubber bands you have holding them together, the more bonds you have tying them together, the stronger they're going to be held together. So the more energy that you have to put in order to break them apart. Okay, so I ask you to take a look at these different compounds here and assign the bond order to the central bond in each of these different atoms, and make sure that the bond length and the bond dissociation energy follow the trends in which we have assigned. So pause your video and go through that on your own. Okay, so we see here the first one has a single bond, so that's a bond order of 1. The second one has 2 bonds between, so that's a bond order of 2. And the third one has 3 bonds between, which is a bond order of 3. And so we can see as the bond order goes up, the bond length goes down, and the bond association energy goes up. So this is data that supports the findings that we have of the inverse relationship between bond length and bond association energy. All right, so covalent bond length indicates the bond strength. So the shorter the covalent bond, the stronger the bond. The longer the covalent bond, the weaker the bond. So the factors that affect bond length, as we said previously, was the atomic radius and the bond order. And so here's a table here that indicates the average bond dissociation energies for lots of different covalent bonds. And the thing to note here is if we're looking at our single bonds here at the top versus our multiple bonds, we can see that the multiple bonds, the double and the triple bonds, are much, much higher in bond dissociation energy, meaning that they're much, much stronger than our bond order 1 single bonds. So I ask you the question, rank the following bonds in order of increasing bond length. So pause the video and work through that on your own. Okay, so the bond length in this problem, we're going to be looking at the atomic radius that's going to indicate our bond length. Okay, so the larger the radius of the molecules involved or of the atoms involved, the larger the larger the bond length that we're going to observe. So if we take a look at the periodic table and classify iodine, bromine, and chlorine is termed in terms of bond radius, we're going to find that iodine is the largest, followed by bromine, and then chlorine is the smallest. So therefore, HI will have the longest bond length, HBr will have the second longest, and HCl will be the third longest. So now when we're talking about covalent bonds, electrons are not always shared equally. So we have 3 different classifications of bonds that we are interested in looking at. So the first is the nonpolar covalent bond, where the electrons are shared equally between the 2 atoms. Okay, and so what we have over here on the right-hand side, these are called electron density diagrams or electron density drawings. And so what we have here is when you have a large red color, that indicates a high amount of negative charge. When you have a blue color, that indicates a high amount of positive charge. And then when you have a greenish yellow color, that means a rather neutral charge. So we can see that molecules such as H2 or Cl2 or CH share their electrons equally between the 2. All right, so those 2 electrons that they're sharing in the covalent bond are centered mostly in the center between those 2 nuclei. So that's called a nonpolar covalent bond. So a separate type of bond is called a polar covalent bond. That's where the electrons are not shared equally. And so we can see in that sort of polar covalent bond that you could have a large electron density surrounding one of the atoms and an electron deficiency around the other. So instead of those electrons being evenly shared between the 2 nuclei, they're all being hogged by one. And so for a polar covalent bond, we could see that between carbon and oxygen, oxygen, hydrogen and fluorine. And so we can indicate a partial positive and a partial negative charge on these specific atoms by using a sigma and an arrow notation. So if we go up to the board and take a look, if we're talking about a polar covalent bond, we could show a bond together, and then we can sort of draw this electron density diagram based on size since we don't have color. So this equally distributed between the 2 would be our nonpolar covalent bond. If we had a polar covalent bond between 2 atoms, what we would do is we would draw sort of a mushroom on the side. So the larger that you have will indicate a larger electron density. So that would be a polar covalent bond. And what this means is that you have a higher negative charge because the electrons are being all pulled by this electron. So what we do is we indicate a partial charge. So partial we indicate with a lowercase sigma. So a partial negative charge and a partial positive charge. And then we can draw an arrow indicating the direction of that polarity. So you can think of this in terms of like a magnet, where we have a positive pole of the magnet and a negative pole of the magnet. So these polar covalent bonds essentially draw themselves, convert themselves as a magnet. So on the positive side of this arrow, excuse me, on the arrow, you draw a plus sign and then point towards the negative. Plus sign on the positive side, pointing towards the negative. So that tells you the direction of what's called a dipole. Dipole will be your direction of your magnet. Okay? And so that's the nonpolar covalent bond, the polar covalent bond. And then we can have an ionic bond, which we already discussed last chapter, is where the electrons are not shared at all. They're actually totally donated from one to the other. And so you can see that in our electron density diagram here, that it's not really an equilibrium. It's just it's a total transfer of that electron. So you have a complete positive and negative charge, not a partial positive, partial negative, like we had for the polar covalent. So what was the factor that leads to this polar covalent bond or a nonpolar covalent bond? How do you know if electrons are going to be equally shared or not? So that brings us up to the topic of electronegativity. So electronegativity is another one of those hallmark topics that are entirely that keep coming back over and over again in general chemistry. And so, just like effective nuclear charge, it would behoove you to really be able to understand and conceptualize electronegativity very clearly. So electronegativity is defined as the tendency for a bonded atom to attract electron density towards itself. Okay, so just a quick note, this is not electron affinity, which is defined as the ability to add an electron. This is the tendency of a bonded atom to attract electron density towards itself. So it's not totally ripping an electron and taking it, it is just pulling it towards it. Okay, and so we have some trends in electronegativity that follow our periodic table. So nonmetals exhibit much higher electronegativity than metals do. And some important things that we have here, fluorine is our highest electronegative atom. Oxygen is our second highest electronegative atom. And hydrogen kind of bucks the trend of the table, and hydrogen goes between boron and carbon. Okay, so you should say that to yourself over and over again when you're studying. Fluorine is the most electronegative, oxygen is the second, hydrogen goes between boron and carbon. Okay, and then to the general trends that we see as we go from left to right on the periodic table, electronegativity increases. As we go from the top to the bottom on the periodic table, we see that electronegativity decreases. And so you can remember that very easily if you remember that fluorine is the most electronegative atom, and cesium in the bottom left corner is the least electronegative atom. So the trends go from there. Okay? And so remember, electronegativity is the tendency of an atom to be able to attract electron density towards itself. So that means if you have a fluorine that's bonded to another atom, so for example, fluorine bonded to a hydrogen, so these numbers here classify the extent in which it pulls that electron density. So the higher the number, the more it's going to pull that electron density towards itself. So the larger the gap between these numbers, the more polar the bond is. So whereas if you have an F2, so two extremely electronegative atoms that are bound to each other, they both are pulling at the same strength. So that would be a nonpolar bond. So let's illustrate this a little more on this next slide by looking at a quantitative term called bond polarity or delta chi. Okay, so if we take these bond polarity numbers that were given to us in our previous plot, okay, all these numbers here, if you take those numbers and you have a bond between two atoms, if you subtract those electronegativity values from each other, you're going to get a result. And so if the result of that subtraction of those two values is between 0 and 0.4, you're going to be talking about a nonpolar covalent bond. So these are going to be bonds where the electron density is shared equally between the two. If you subtract the two and you get a value between 1.4 and 1.8, then you're talking about a polar covalent bond, where the larger the number, the more unequal that electron density is being shared. And then the bigger your magnet is, the more partial negative and partial positive charge that you have. And then if the value of the subtraction is greater than 1.8, then you're talking about a complete transfer for an ionic bond. Okay? And so it's important for us to be able to actually do that mathematical treatment, but it's also important for us to be able to just do an eye test. So if we're taking a look and assessing bond polarity, the further apart two atoms are from one another, the more likely they are going to be polar. And for identifying an ionic bond, we know an ionic bond from the last chapter is between a metal and a nonmetal. So we can readily identify that. But as for a polar covalent versus a non-polar covalent, if we're talking about, say, fluorine to a hydrogen, those are pretty far apart from each other. So we know that that's going to be most likely a polar covalent bond. Or fluorine and a carbon are pretty far apart. Those are going to be polar. A carbon and oxygen, those are pretty far apart. And we know oxygen is very highly polar, so that's going to be a polar covalent. Okay? Whereas direct neighbors, if we have like a sulfur and a phosphorus, those are direct neighbors to one another. So chances are that that's going to be less of a chance of being a polar covalent bond. That'll more likely be non-polar covalent. Okay? So it's important for us to be able to calculate delta chi, but also to be able to just kind of use our eye in a judgment test. And so this may seem very arbitrary right now, but we're going to get more and more practice of this, and I promise it'll become second nature for you. So let's take a look at using our actual numbers and to determine the bond polarity of um, the following molecules. All right, so pause the video and work through these, determine the delta chi, and then assign each as either nonpolar covalent, polar covalent, or ionic. Okay, our first pair is H to H. And so if we find the values of the two, we have 2.1 minus 2.1, and that equals 0. And if we're between 0 and 0.4, that says we are nonpolar. CH. So when you're subtracting the two, you want to have the larger electronegativity of the two come first. So you have 2.5 minus 2.1. That's going to give us 0.4. And so that's right on the cutoff line. So we'll call that actually nonpolar. Okay, the next is NH. All right, and we take a look here, and we find that nitrogen has a value of 3, hydrogen has a value of 2.1. So we have 3.0 minus 2.1. That gives us a value of 0.9. And so since that's above 0.4, that's going to read out as a polar covalent bond. And so which one of these two atoms is going to actually be pulling the electron density? It's going to be the one that has the larger electronegativity. So we can say that the hydrogen is going to have that partial positive charge, and nitrogen is going to have the partial negative. So sigma negative, sigma positive. And we have the arrow pointing from the hydrogen to the nitrogen. And finally, for NaCl, we know that this is a metal and a nonmetal. We know it's going to be ionic, but let's just prove with the math. Chloride has a 3.0, and sodium has 0.9. So we have a value that's 2.1, which shows that we are ionic. So we have a total plus and a total minus. Okay, so next, rank the following bonds in order of increasing bond polarity without having the exact electronegativity numbers. So I want you to pull out your periodic table and take a look at where each of these atoms are showing up in the periodic table, and then make your best estimate on whether this is going to be a polar covalent, nonpolar covalent, or ionic. Okay, so the first one, ClCl. So we can see that these guys here are the same atom. So regardless of the value, if you take of the electronegativity, if you take two electronegativity values, they're subtracted from each other, they're going to equal to 0. So that means it has to be nonpolar covalent. All right, Kf. So we know that potassium is a metal. It's located on the left-hand side of the periodic table. And fluorine is a nonmetal halogen. So we know when a nonmetal and a metal combine together, we have to form an ionic bond. Next, carbon to fluorine. All right, so we know that fluorine is the most electronegative atom on the periodic table. So pretty much fluorine combining with any other atom except for itself is going to give you a polar covalent bond. The only thing you have to watch out for is to make sure that it's not bound to a metal, which makes it ionic. So since it with a carbon and the carbon and fluorine are separated rather far on the table, that's going to be a polar covalent bond. And the fluorine is going to take the electron density. So we'll have the partial positive on the carbon and the electrons going to the fluorine. So partial negative, partial positive. Okay, finally, CO. So we know that oxygen is the second highest electronegativity on the periodic table. So we know that it's most likely that that's going to form a covalent bond as long as it's not bonded to itself. And so we know that the electron density is going to be pulled towards that oxygen. So that'll give us a partial negative and a partial positive. Again, polar covalent. Okay, next. The electronegativity is 2.1 for hydrogen and 3.0 for nitrogen. Based on these electronegativities, NH3 would be expected to be which of the following? To be ionic because it contains H minus ions, to be ionic and contain H plus ions, to have polar covalent bonds with a partial negative charges on the H, to have polar covalent bonds with a partial positive charges on the H, or E, none of the above. Okay, so work through that for a second. Okay, if we're going to draw this NH3, we're going to have the nitrogen in the middle, and we're going to have 3 hydrogens bonded to it. Okay, and if we look up on the table here, it's actually given to us in the problem. If we calculate delta chi, we get a value of 0.9, which tells you that each of these bonds are going to be polar. And so we have a directionality going with the electron density residing in the middle nitrogen atom. So we have this large partial negative in the nitrogen and then partial positive with all of these hydrogens. All right, so the correct answer here, the correct answer here would be D, where we have a polar covalent bonds with the partial positive charge on the hydrogen atoms. All right, our last slide here is another review question for you here. Which of the bonds in this chlorofluoromethanol is the most polar? A, B, C, D, or E? So take a moment to look at that. Okay, the correct answer here is A. All right, so the reasoning is, so we're looking for which two atoms here are going to be furthest apart on our periodic table. Okay, and also knowing that oxygen is the second highest electronegativity atom. Okay, so if we take a look, we know that hydrogen is going to locate itself between boron and carbon on our periodic table. And so that means it's going to make it pretty far away from that oxygen atom, which is going to make that bond the most polar in comparison to all the rest. All right, with that, that's it for the day. Thank you.